Take a second and think about the chair you're sitting on. Feels pretty solid, right? Well, what if I told you it's actually mostly empty space? Yeah, seriously. Today, we're going to dive into the hidden, microscopic universe that makes up everything around us. Let's get started.
So it all kicks off with this really simple puzzle. Think about it. You can pile up sand, make a sandcastle, right? But you can't do that with water. Why is that? This one little question, it's the key to unlocking the very nature of matter. And trust me, by the end of this, you'll have the answer. All right, to crack this mystery, we've got to put on our scientist hats. And you know what that means? It means we start breaking things down. So let's head over to our imaginary lab and grab a really common, everyday object.
Okay, so we've got a stick of chalk. First, we snap it in half. What do we have? Still chalk, just smaller pieces. Now, let's get serious and grind it all the way down into a fine powder. If we stick that powder under a magnifying glass, what do you see? Each tiny, tiny speck is still, fundamentally, chalk. And this whole process brings up a really big question. I mean, could we just keep grinding and grinding forever? Or is there a point where we hit rock bottom? A single tiny piece of chalk that you just can't break down any further? Well, it turns out there is a limit. And that fundamental, totally unbreakable unit, that's what we call a constituent particle. It's the ultimate building block. That whole stick of chalk we started with, it was really just a massive, massive collection of these teeny tiny particles. You know, what's really cool is that this idea isn't new at all. I mean, centuries ago, an ancient Indian philosopher named Acharya Kanad was talking about this. He proposed that all matter was made of these tiny, indivisible particles he called parmanu. So we're tapping into an idea that has fascinated people for ages. Okay, so quick recap. Everything is made of particles. Got it? But believe it or not, that's only half the story. If we really want to understand matter, we've got to uncover the hidden rules that tell these particles what to do. So here's our next clue. Picture this. You stir a spoonful of sugar into a glass of water. The little white crystals just vanish. But you take a sip, and the water is definitely sweet. So the sugar is still in there, but where did it go? It didn't just disappear, right? And this little disappearing act reveals our first hidden rule. When that sugar dissolves, it's actually breaking down into its individual constituent particles. And those super tiny sugar particles, they slip right into the empty spaces that exist between the water particles. See? They're not gone. They're just hiding out in the gaps. This idea has a name. It's called interparticle space. It means that matter isn't a solid continuous block. Nope. There are tiny gaps between all the particles. This is that aha moment that explains how stuff can mix together and dissolve. And yeah, it's also why that chair you're sitting on is, on a crazy microscopic level, mostly empty space. But wait a minute. If there are all these spaces between particles, what stops everything from just floating apart? That brings us to our second rule, interparticle attractions. You can think of it like an invisible cosmic glue that holds all the particles together. And the strength of this glue, well, that changes everything. Okay, now we've got our complete scientific toolkit. We know about particles, we know about the spaces between them, and we know about the forces holding them together. With just these three simple concepts, we can finally solve our original mystery about the sand and water, and explain the three states of matter. First up, let's talk solids. In a solid, the particles are packed in there super tightly, like a sold-out concert. The spaces between them are minimal, and that invisible glue, the attractive force, is incredibly strong. It locks every particle into a fixed position. They can't go anywhere. All they can do is just kind of vibrate in place. And the result? A definite shape and a definite volume. Simple. So how is that different from a liquid? I mean, the most obvious difference is the shape, right? A solid holds its own shape. But a liquid just flows and takes the shape of whatever you pour it into. And that difference comes directly from how their tiny particles are behaving. See, in a liquid, the particles are still pretty close together, but the attractive forces are weaker. That glue just isn't strong enough to lock them down. This lets the particles slide and tumble and flow right past one another, which is exactly why a liquid takes the shape of its container. They're still hanging out together, just way more casually. You know, this same logic explains something else you've definitely experienced. When someone sprays perfume or lights an incense stick, that smell doesn't just stay in one spot, does it? It travels all the way across the room.
And that happens because that fragrance is a gas, our third state of matter.
Now, in a gas, it's a completely different ballgame. The particles are so far apart and moving so incredibly fast that the attractive forces are basically zero. They have practically no glue holding them together. They are totally free to just fly around randomly in every direction, filling up any and all available space. And that's why gases have no fixed shape and no fixed volume. Here's a super simple way to feel this difference for yourself. Grab a syringe, one without a needle. If you fill it with air and plug the end, it's pretty easy to push the plunger down, right? That's because you're just squeezing all that huge empty space between the gas particles. But now, try doing the same thing with water. It's nearly impossible. Why? Because the liquid particles are already packed in there nice and close. Okay, let's bring this all home. We've just uncovered the fundamental rules that run our entire physical world, and it all started by asking a simple question about why you can't pile up water like you can with sand. It really all just boils down to the spacing and the attraction between those tiny little particles. This chart here just lays it all out perfectly. Check out the pattern. As you go from a solid to a liquid to a gas, what happens? The space between the particles gets bigger, the attraction between them gets weaker, and their movement becomes way more free. It's a really clear, predictable relationship. So, what's the one thing that's actually driving all these changes? Well, it all comes down to energy, specifically thermal energy, or, heat. The more heat energy you give to particles, the more they wiggle and move, and the easier it is for them to overcome those attractive forces holding them together. Heat is what lets a solid ice cube melt into liquid water, and that liquid water boil away into a gas. And that brings us to one last thought to leave you with. Your chair is a chair because of a very specific arrangement of trillions and trillions of tiny particles. So, if we could somehow just snap our fingers and make every single one of those constituent particles vanish, what would be left? Absolutely nothing. The chair wouldn't just be lighter, it would simply cease to exist. Kind of makes you think, doesn't it?